So what we're going over today in this lecture is something called the voltaic or galvanic cell. You'll hear both words, they're both synonyms, and of course we'll say the galvanic, or the better used term is voltaic cell. These are examples of electrochemical cells. These are, of course, batteries. Okay, now Luigi Galvani and Alessandro Volta, two Italian physicists, or I would say Volta was a physicist and Galvani was a biologist. These two scientists collectively are responsible for the development of the battery. Very quickly, Luigi Galvani was using basically static electricity to shock the legs of of frogs, unfortunately, and saw that their movement was due to electrical input. And Volta, and of course Luigi Galvani, suggested that that input electricity was biological in nature, and Volta suggested that, well, electricity, or this static electricity, or this motion due to biology, is basically found in all physical parts of the world, not just exclusive for biology. So he built a battery to prove that. So the combination of their arguments, whether electricity was biological or something that was physical in nature in all parts of science, led to the first battery. So in any case, that's where the words come from. So when you hear voltaic cell or galvanic cells, that's what this describes. Now, of course, a battery is a spontaneous redox reaction where there is a flow of charge that's able to do useful work. We run all kinds of things with batteries, so it's very spontaneous. Okay, my discussion here is mostly on the honors and Regents level discussion here, but choose as you may to use this. Okay, any case, when I look at a battery, which is split in two half reactions, or sometimes called half cells, right? You've been writing half reactions. So a half cell, okay, sometimes is called a cell itself. So the half cells are the half reactions. So if you split the compound, or the half of the redox reaction that oxidizes from the one that reduces, and apply a conducting wire that connects them, you can have a flow of charge. Any case, the first step in dealing with this setup is to identify some important piece or important components. The first component is the anode and the cathode. Okay, if you haven't already learned, there's a nice mnemonic, anox, red cat, and that's probably on top of your Leo the lion, says grrr. So the anode is the place of oxidation, where we're losing electrons, and reduction is the place of reduction is the cathode. Okay, so you'll hear the word electrodes. So the electrodes, okay, are the actual physical place where the redox reaction can occur and where electricity or charge is conducted through in each half cell. Sometimes they're involved in the actual redox reaction, and sometimes they are not. So let's start this, okay, by identifying our electrodes as either the anode or the cathode. The first step, let's look at our two electrodes. Okay, we have zinc and we have copper. Of these two metals, the absolute first step is to find our anode, because finding our anode will find the origin of the charge and the flow of charge. So I have to evaluate zinc and I have to evaluate copper. Who is better at losing electrons? Who is better at oxidizing? So what I can do is go to a net potential table, okay, and I can see where zinc is and where copper is. All right, so I've just found my zinc, and there she is, and my copper, okay, well below that, okay, right here. So I look at zinc, and its oxidation potential is positive 0.76, because I'm going in the reverse of reduction, And copper's oxidation potential is positive 0.34. I'm sorry, negative 0.34, since I'm flipping the sign going in the opposite. Okay, so this is going to be a positive value here. All right, in any case, so zinc is a more reactive metal, as you probably can guess. All right, so zinc is the anode. Now, if we're using table J for the New York State regions, which is, again, a poor table that basically has its origins from net potentials, okay, we can see the same thing. Zinc, okay, is higher on this reactivity table than copper. So this is a list of metals' reactivities. Metals are active or reactive by losing electrons. Basically, this is a list of how well metals oxidize. The best metals that oxidized are higher, and the metals that oxidize the least, or the least ability to lose electrons, are on the bottom. Here is your gold, okay? If you see how gold stays shiny because of its lack of ability to oxidize, at least in the presence of chemicals that exist. So going back to our little drawing here, we see that zinc is the place of oxidation. So this is the oxidation half cell. Oxidation occurs here, the loss of electron. Thus, reduction has to occur here. Now, I didn't fully explain my drawing. In the zinc half cell, we're going to have zinc plus 2 ions. So you could probably see something like this. You can say, hey, I have zinc nitrate written. We know nitrates are soluble, and here we'll have copper nitrate. I'm sure your teacher or myself will be demonstrating this Danielle cell, very simple battery cell. Now, the zinc nitrate means you have, well, you have NO3 minus, and you've got zinc plus 2 in solution. Over here, we've got copper plus 2 in solution, and we have NO3 minus. These are important electrolytes, okay, and they're important for balancing the charges. We'll talk about a little bit later in this lecture. Okay, so what's going to happen in this half cell? And well, in this half cell, oxidation is going to occur. Now, I identified this as my anode because it was the electrode, okay, the conducting place for redox to occur on here, or in this case, where oxidation can occur, because remember, we talk about anox here. The anode is the place of oxidation, and because zinc was a more reactive metal than copper, better at oxidizing for whatever table you use, okay, then zinc is my anode. So therefore, this has to be my cathode, and this is the place of reduction, red cat. Okay, now specifically, what is oxidizing? Well, the zinc 0, and you should know that metals that have no charge are solid, with the exception of mercury, are going to become the aqueous ion plus 2 electrons. So what's really going to happen is a piece of this zinc solid, okay, is going to become zinc plus 2. Okay, and as that happens, it pushes these electrons through the wire to the copper. And we can say that they kind of build up here if you want to suggest that. Now we know electricity really is the flow of charge, but I'm just using that analogy if you want to get technical. Now the copper plus 2, okay, this, I should say, sorry, this half cell here is the reduction half cell. Now what's reducing here? Well, you may say, Mr. Grotsky, copper can't reduce. You're right. No metal that is a solid in a 0 state reduces. We don't have negative oxidation states. You can't find a metal that becomes negatively charged. So the copper doesn't actually take place, or is not part of the actual reaction or half reaction. It's really the place where the oxidation, or in this case, the reduction occurs. In this case, the zinc actually is, this electrode, the anode here, is actually taking part in the oxidation. Okay, and that'll be the case in a lot of these very simple cells. But some electrochemical setups, galvanic or other, okay, will have electrodes that are not part of the oxidation reduction themselves. This is an example. So the copper cannot reduce. So what happens is the copper plus 2 ion is the one that specifically gets reduced. So it's the copper plus 2 that gains 2 electrons to become copper 0. Okay? And if you look very carefully, the copper plus 2 already in solution, we put this solution in here, okay, gains the 2 electrons that are forced upon. Now you may say also the copper plus 2 pulls the 2 electrons. So copper plus 2 pulling the charge this way and the zinc pushing the charge this way gives a force of charge along this wire, and that's what a volt is. It's a potential difference of charge. Okay, it's the energy that moves the coulombs of charge of electrons around. All right, so important to also realize we just made solid copper. Anytime you've got a metal that's a 0, we made solid copper. So the copper plus 2 gains the 2 electrons and it plates. So this electrode, although not part of the actual reduction, is the place where reduction occurs, gets bigger because plating occurs. So copper plus 2 grabs onto electrons and plates. Every time what? A zinc, okay, becomes zinc plus 2 and sends electrons. So this zinc metal is getting smaller. A metal, remember, a metal that's 0 is solid, becomes an aqueous ion when it pushes 2 electrons through. And this aqueous ion becomes a solid metal, okay, as it pulls electrons or it gains those 2 electrons that come from the oxidation cell. Now something you can always realize here, the flow of electrons or the flow of charge is always going to be, always, no matter what we do here, from the anode to the cathode. So the flow of electrons always from the anode to the cathode. And that's something we always explain, and it kind of makes sense. The anode is the place or the origination, the origin of where charge comes from, or charge is being pushed on, or electrons are being released. And the cathode is the destination where electrons are absorbed or pulled along. So these are releasing, these are absorbing. It kind of makes sense. You can't have a cathode going to an anode because if the cathode is absorbing electrons, these are releasing. It just doesn't make any sense. So the next part of this for my honors or AP kids would be to come up with a total overall electromotive force or net potential, standard potential of the reaction. Now for my Regents kids or anybody else taking a course that does not have these potentials, you can just continue on or fast forward. But here's what I'm going to do. Put the half reactions together. I've got zinc 0, okay, as we've done before, zinc plus 2 electrons, and then I've got my copper, my reduction half reaction, copper plus 2 electrons gives me my copper 0. Okay, now I'm going to ask, like an AP or an honors, what is the maximum potential for a voltage here? Or at least, what is the standard if we use standard conditions? So we would go to our net potential table. Okay, you really can't use table J here. This is not part of Regents, but it's fun to look at. And we're looking at copper plus 2 reducing, and since the reduction tables go exactly as they're written, it's a negative 0.34. And look at zinc, okay, oxidizing, because it's going in the reverse, it's positive 0.76. All right. Some teachers will teach you to find the net potential. It's cathode minus the anode, and that will also work. The minus the anode would switch this sign. Okay, so in any case, we're going with reduction, so positive 0.34 and a positive 0.76 because we're going in the reverse. So back to our drawing. Okay, positive 0.34, 4 volts, and a positive 0.76 volts. Now, if you notice something, okay, they're both positive, which means both half reactions are very spontaneous. If you think about it, there's a collective effort to push charge around, to give energy to push this charge around. The zinc spontaneously, because it oxidizes very well, okay, by itself produces a potential of 0.76. The copper plus 2 by itself produces a potential of positive 0.3 volts. So when we collectively think about the total energy pushing charge around, we add these together and we get 1.10 volts. Okay, and this is about the same as in a AA battery. Okay, all right. Notice in our half reactions, electrons cancel. All right, the total, okay, overall reaction would be zinc 0 plus copper plus 2, go to zinc plus 2 plus my copper. That's the overall reaction. Okay, and you should know who got oxidized. Okay, the zinc 0 specifically was better, so that it got oxidized. Who specifically got reduced? Okay, who gained electrons? Grrr. Copper plus 2 did. And for those that don't understand, a copper plus 2 is absorbing 2 electrons here. Okay, now agents. Who is the oxidizing agent? Now here, agent, think opposite. Who got reduced? Copper plus 2. Copper plus 2 pulled electrons or charge from zinc. Who is the reducing agent? The one who got oxidized, zinc 0. Notice the answers to my questions are always on this side. Okay, and that's essentially your table. Now there's one important piece here that I have left out for the end, and if you cut this off without finishing, you missed out on something. If you notice, there's a YouTube sitting here. Right now, although I should be getting 1.10 voltage, if I did not have this here, okay, it's something called a salt bridge. If I didn't have the salt bridge, there'd be 0 voltage. Every battery has to have a way to electrically balance the charge in the solutions. We want electrons to flow through the wire. Electrons do not flow through this to YouTube, okay, or the liquid here. Let me explain what the salt bridge does. Out of salt bridge, you get 0 volts. So you need the salt bridge. And I will show you, or I have shown you, taking the salt bridge in and out of a Danielle cell or battery will make the voltage go to 0. Now, what does it do? Well, if you look carefully, zinc gives off 2 electrons. So if you notice, over time, zinc plus 2 is building up. So this half cell becomes positive. Now, just by convention, we call the anode, or give the anode, a negative charge. All right? And just by convention, we give the cathode a positive charge, okay, to show that negatives flow through a positive. Okay? Now, that's what we say. Now, if you, over time, if zinc plus 2 builds up, this half cell does not stay negative. It becomes positive, and electrons won't flow away from a positive, right? If I'm negatively charged and I was just released by zinc, why would I flow away from something that I'm attracted to? So we have to have a way to keep this beaker from getting positive. So a salt bridge allows this to happen. A salt bridge, okay, made up of some salt who has positive, negative ions. The negative part of that salt bridge migrates down to counterbalance the positive charge that are building up. So what happens is Cl negatives, all right, come into this beaker to balance off the positives. So for every zinc plus 2 given off, 2 Cl negatives will migrate down to keep this beaker electrically neutral so that electrons are not attracted to it and they can flow. On the other side, if you've guessed it, copper plus 2 is being lost. This beaker needs to stay positive, or at least we say it's positive, okay? So we're losing positive charge here. For losing positive charge, as it does what? As it reduces and gains electrons and plates, this beaker starts to become negative. Electrons won't flow to a negative. So what happens is the positive ion, okay, migrates down here to offset the loss of positive by the copper plus 2. So 2 Na pluses would migrate down for every copper plus 2 that's lost to keep this beaker electrically neutral. Okay, only ions flow here. Now, in truth, since this side is gaining positives, you could also make the case that, okay, that nitrate ions that were originally in the solution, okay, because of the copper nitrate, can also migrate through the salt bridge and come out here. Why would they want to migrate? Well, this negative could travel through the salt bridge and be what? Attracted to the increase in positives. The bottom line is the salt bridge allows electrolytes, ions, to flow in both directions so that each of these beakers stay electrically neutral. Okay, even though we put a charge, okay, on them, all right, to describe by convention anode and cathode, these beakers are electrically neutral, and a salt bridge maintains that neutrality so electrons can flow. Okay, and that is essentially all the components of a galvanic or voltaic cell that you will need to know. Of course, Regents level, we're not going to do net potentials and get a voltage here, but everything else I discussed is fair game. Hope this helped.